I'm going to start the 8.8 section 8.8 improper integrals. So this is the last section for this chapter. We're going to talk about one more topic. It's called improper integrals, and it refers to typically two situations. All right, so let's talk about proper integrals. Okay, then we can talk about improper integrals. So an integral of f from a to b is proper if the closed interval ab is finite. Okay, you just integrate the function on a finite interval on the x-axis. That means you try to find the area under curve. Remember, the definite integral is the area under the curve. So you're trying to find the area under the curve where the base, of the area is finite. Okay, and also fx is continuous on the closed interval from a to b. So you don't have any jump, you don't have any vertical asymptotes. Okay, it is continuous from a to b on the closed interval, so that includes the endpoints also. Okay, you cannot have, for example, vertical asymptotes at the endpoints a or b. Okay, so if that's the case, then we have a good situation to deal with the integral, and we don't have to worry about the integral. You can always find the area under the curve, in this case, to be finite. All right, but there are some cases that when the area you try to find under the curve is extended to the far right or far left, or on the whole horizontal axis. You want to try to find the area of a non-tail. So for example, if you integrate function f from a to infinity, what does it mean? It means you want to find the area under the curve on the right of a. So there's a long tail on the right, and you want to find the area of this tail. And the way to integrate it is, because the infinity is not numbered, and you cannot plug in after you find the antiderivative of f. You cannot plug in the infinity symbol into the antiderivative to evaluate, because it's not a number. So what you do, you convert this problem to a limit. So you just integrate the function f from a to b, where b is a finite number. Okay, so then we can integrate it as usual, and then you can plug in b into the antiderivative, right? And then you let b approach infinity and take the limit, and then that will give you the answer for this problem. And that's called an improper integral, because now we got the base approaching infinity. Okay. Similarly, if you want to find the integral of f from negative infinity to b, it means you want to find the area under the curve on the far left up to b, right? So there's a long tail on the left, and this time we're going to integrate the function from a to b, where a is any finite number on the left of b. And then you just let a approaching infinity and negative infinity and take the limit. So you just move a to the far left, and it becomes a problem of a limit after the integration. So that's another situation And sometimes you might need to find the area on the curve of f for the whole horizontal line, okay? So there are tails on both ends. And then in this case, you have to break the integral into two parts. Just cut the whole area on curve by two parts anywhere, okay, anywhere. So you integrate the function f from negative infinity to c, so that's the left-hand part of the area, and plus the integral of f from c to infinity. That's the right part of the tail. So you can cut anywhere, okay? This number c can be anywhere, any number, it doesn't matter. You're going to get the same answer, okay? So that's the definition of improper integral with infinite limits of integration, all right? So we got the limits of integration, a and b are called the limits of integration, remember? This a and b. But when you have infinite limits of integration, you have b approaching infinity or a approaching negative infinity or both approaching infinity or negative infinity. Then we got the first type of improper integral, all right? So that's the integral with infinite limits of integration, all right? I think I draw some pictures. So it didn't show up in here. I don't know why, but anyway. Let's do some examples. So let's try to evaluate the integral of 1 of x from 1 to infinity. So that is an improper integral with infinite limits of integration because the upper limit of integration is infinity. So that's this type. Improper integral. So the way to do it, by definition, is to convert this problem to a limit. So what you do, you integrate 1 of x from 1 to b, and then you take the limit of the answer with b approaching infinity. So then it becomes a two-step problem. First, you integrate. The second step is you take the limit. So if you integrate 1 of x, you get the natural, the absolute value of x, and then just integrate as usual from 1 to b. So you get the natural log of absolute b minus natural log of 1, right? And then you do the second step with b approaching infinity, okay? We know natural log 1 is 0. And then you just need to find the limit of a natural log of b when b approaches infinity. Okay, so on the right side is the curve of a natural log function. Okay, so when you try to find the limit of a natural log of b in the answer in the step, then you look at the curve of the natural function on the right. So the red curve on the graph just keeps going up without bound. So that means the limit of natural log b as b approaches infinity is infinity. Okay, so the red curve, goes up on the right without limit, without bound. So we say the improper integral diverges because this improper integral of 1 of x from 1 to infinity results in infinity. Okay, that means if you think about the area of the curve of y equal to 1 over x from 1 to infinity, you try to find area of this curve on the region under the curve. It turns out the area is infinity. Okay, all right. Any questions for this example? No question, then let's do another example. So this time we need to do a improper integral of e to the negative x from 0 to infinity. Again, this is improper integral with infinite limits of integration, the same type. So again, it breaks up into two steps. First, you just integrate the function e to the negative x from 0 to b. Okay, I find the number b, and then you let b approach infinity and take the limit. So we can easily uh, yeah, integrate e to the negative x, and you get the negative e to the negative x. Okay, and I just say, write a hint here. You need to use a substitution for u equal to negative x in order to get the negative e to the negative x from e to the negative x when you integrate. And then you plug in b and 0 for x and subtract, so we got the limit of with b approaching infinity of e to the negative b minus negative e to the negative b minus negative e to the negative 0. Okay, I got too many parentheses, probably. It should not be so many. Okay. Anyway, it becomes negative e to negative b plus 1, so you got two negative sign in the second term, and e to negative 0 is just 0, and e0 is just 1, so we get plus 1. Well, so this time we need to evaluate the limit of negative e to the negative b with b approaching infinity, and then the function of negative e to the negative x or negative b is showing on the graph. So the blue curve. Okay, so as b approaching infinity or x approaching infinity, function itself approaching 0, right? Okay, the curve approaching 0, the function value of the curve approach 0. So the limit is 0 for the first term, and then you get 0 plus 1. So the final answer is 1. So this time we do get the final number for the answer of this improper integral. And we say the improper integral converges. Okay, so you got the finite number. So we say it converges. If you don't get the finite number, we say it diverges, as in the previous example. All right? Any questions on this problem? No question. Okay, then let's do one more problem. Okay, this time it becomes a little more complicated. Okay, we need to evaluate the integral of e to the x over 1 plus e to the 2x from negative infinity to positive infinity. So this time we got another situation where both the upper limits of integration for this integral are infinity. Actually, one is negative infinity and the other is positive infinity. So as we said before, we need to cut this integral or the area on the curve or this function into two parts. Namely, we need to integrate function e to the x over 1 plus e to 2x from negative infinity to a number c. That number c can be any number. So here, choose 0. Sometimes it makes it convenient to compute when you choose 0. And then plus another integral from 0 to infinity of the same function e to the x over 1 plus e to 2x. And then you just use the definition of two improper integrals. You got two improper integrals, and they use the definitions previously, and they just do it. So the first integral with a function from negative infinity to 0, you are going to replace negative infinity in the lower limit of integration by a, and integrate the function from a to 0, and then take the limit with a approaching negative infinity. Okay. And for the second part, you replace the positive in the upper limit of integration from infinity to b, and then you take the limit of the answer with b approaching positive infinity. Okay. So if you integrate e to the x over 1 plus e to the 2x, you're going to get the arctangent e to the x. So in both the integrals, you get the same thing, arctangent e to the x. So to integrate to the x over 1 plus e to 2x, you need to use the substitution u to the e to the x. Okay, so I'm not going to show the details about that. You should check yourself. But if you use that substitution and evaluate the integral, you're going to get arctangent e to the x for both functions. So in the first term, you got a from a to 0 and take the limit with a approaching negative infinity. And in the second term, that function arctangent e to the x, from 0 to b, and then take the limit of the result with b approaching past infinity. Okay, so then so just do it term by term. So in the first term, you get arctangent e to the 0 minus arctangent e to the a. Remember, that's how you plug in. And then take the limit approaching negative infinity. And in the second term, you got an arctangent e to the b minus arctangent e to the 0, and then take the limit with b approaching past infinity. Okay, so e to the 0 is just 1. So you get arctangent 1 minus arctangent e to the a in the first term, and take the limit a approaching negative infinity, and similarly in the second term, e to the 0 is 1. So you get arctangent 1 with arctangent e to the b minus arctangent 1, and you limit with b approaching infinity. All right, arctangent 1 is just powerful. Okay, that is the angle which results in 1 for the tangent function. Okay, that's powerful 45 degrees. So you plug in arctangent 1 by powerful in both terms. Okay, and then you need to take the limit from arctangent e to the x or a with the a approaching negative infinity, and the arctangent e to the b with b approaching infinity. Okay, so on the right side, I just draw the curve of arctangent e to the x. So in the first term, we define the limit of this function with a or x approaching negative infinity. So you look at it on the left, and the function value approaches 0, the horizontal axis. So you get 0 in the first part, this power 4 minus 0, the first limit. And then in the second term, you got power 2. Okay, I didn't mark in here, but if you look at the green curve on the right, it flies at 1.57, below 2. Okay, that's the value. The function approaches as x approaches infinity on the right. So that's power 2. So then you get the power 4 minus 0 plus power 2 minus power 4, and the answer is power 2. So this improper integral converges. You get a finite number for this integral. The integral of e to the x of 1 plus e to 2x from negative infinity to positive infinity. So that's convergent or converges. Okay. Okay, so that's the first tab, and then I don't know why I got two twos in here. Okay, some typos in here. Sometimes it's just because the format just mess up a little bit. Of point. So let's talk about the improper integrals with infinite discontinuity. So that's the second type. So what we have done so far is this first type of improper integrals. You got infinite limits of integration, either from a to infinity or from negative infinity to b, or from negative infinity to infinity. To integrate a function, on that. And then we got another situation in the type 2. So this time, the function has a tail on the top instead of on the left or on the right. This time we consider the tail on the top if you look at the graph. So suppose that f has an infinity discontinuity at x equal to b. Okay, so there's a vertical aspect for the curve. All right, so So we call it infinite discontinuity because the function is not continuous here, and the function value approaches infinity at the asymptote, okay, at x equal to b. So how do you integrate the function from a to b? So basically, again, we try to find the area under the curve from b. So you get a long tail on the top instead of left and right? So what I do again, you change the problem into two steps. First, you just integrate the function from a to c. So they shaded the area from a to c. So that we can, that's the proper integral that we can integrate in the usual way. Okay, there's no problem with that. And then you just take the limit with c approaching b from the left. So you integrate from the function from a to c. And then you move the right boundary c to b, okay? Just push, the right boundary to b. So you take the limit with c approaching b from the left. C is on the left of b. Okay, that's how it means by the one-sided limit. Remember? Okay. And there's another case. Okay, this time we got the function has a infinite discontinuity at x equal to a instead of b. Okay, this time we got the vertical asymptote of the function on the left side. Okay, so we want to find the area on the curve of the function from a to b again, and the a is a vertical asymptote for the function. So what do you do? You're going to integrate the function from C to B, find the area from C to B, okay? And then C is between A and B, and then you just push C and the left boundary to A. So what do you do? Just integrate the function from C to B, and then take the limit of C approaching A from the right. So you put a plus in here. So that's the right-hand side of the limit. Okay, so again, that's a two-step problem. Okay. Well, there are some other situations where you have a function, with vertical asymptotes from both sides. Okay, like this in the example. So we have function has an infinite discontinuity at x equals to c, where c is inside of a and b, and you want to find the area under the two curves from a to b. Okay, so then obviously you have to break up into two sub-integrals, one from a to c and one from c to b. And for each sub-integral, you have to use the previous definitions for them. Do it two steps and take the limit. Okay, so this turns out into two integrals, two improper integrals. All right, so it's more complicated. So let's just do some examples of this second type improper integrals with infinite discontinuities. Okay, so we can evaluate the integral of 1 over cube root of x from 0 to 1. Okay, so obviously the function f has an infinite discontinuity at x equal to 0. It has a vertical asymptote at x equal to 0. So if you plug in 0 for x in 1 over cube root x, it doesn't make sense. It's undefined. There's a vertical asymptote. So we got the second type improper integral in this case, and the vertical asymptote is on the left. So what we need to do, we replace 0 by c and the vertical asymptote by c, and then you integrate the function from c to 1, and then you just take the limit with c approaching 0 from the right. Okay, so you push c to 0 from the right. So that's easy to do if you rewrite 1 over cube root x, you get x to the negative 1/3. is in the denominator, so that's negative, but the cube root is 1/3, right, in the exponent. And then you just use the power root to integrate this function. You get x to the negative 1/3 plus 1 over negative 1/3 plus 1 by the power root. Okay, then you simplify it. You get the 2/3 in the denominator, and then you flip it, you get the 3/2. And in the exponent, you get x to the 2/3, and then plug c and 1, subtract, and then take the limit. So we get limit of 3/2 times 1, 2/3 minus 3/2 times c to the 2/3, and then take the limit with c approaching 0 from the right. So in the first term, 1 to the any power is just 1, so we get it 3/2 times 1. And in the second term, c to the 2 over 3, and c approaching 0, so you're going to get 0 for this term, okay? And then multiply by 3/2, you get 0. So the final answer is 3/2, okay? Remember, c to the any positive power has the limit 0 if c approaching 0, okay? So that's the first example. Let's do another one for the second type of improper integrals with infinite discontinuities. Again, we're talking about vertical asymptote for the integrand, the function you try to integrate. So we need to evaluate the integral of 1 of x cubed from 0 to 2. So again, the function 1 of x cubed has an infinite discontinuity at x equal to 0. That's a vertical asymptote. In other words, if you plug in 0 for x, you get the function undefined. There's a vertical asymptote of the function at x equal to 0 as shown in the graph, okay? So again, just do it step by two steps. So you replace 0 by c in the lower integration. You integrate the 1 of x cubed, and then you take the limit with c approaching 0 from the right. Okay, so again, the vertical asymptote is on the left at 0. Okay, x equals 0. So rewrite 1 of x cubed as x to the negative 3, and using the power rule again, you get the x to the negative 3 plus 1 over negative 3 plus 1 when you integrate it. So that becomes negative 2 in the denominator, and also the exponent becomes 2. Okay, so you can rewrite the x to the negative 2 as 1 over x squared, remember? And then you plug in 2 and c and subtract, and then you take the limit. Okay, so what we get is the limit of negative half times 1 over 2 squared if we plug in 2 for x, and the minus negative 1/2 times 1 over c squared if we plug in c for x, and then you take the limit with c approaching 0 from the right. Okay, plus in here. So the first term ends with 1/8. Okay, 1 over 2 squared is 1/4, and multiply negative half, we get the negative 1/8. And then there are two negative signs in the second term, so that becomes positive, and then 2c squared is in the denominator. So now this time c approaches 0, and c is in the denominator. So you get the infinity, positive infinity. Okay. Remember, when you divide 1 by a small number, you get a large number. Okay. So the answer is infinity. So this improper integral diverges. Okay, you don't get the final number. All right, so that's this one. Let's do one more example for improper integrals of the second type, or with infinite discontinuity. So this time we need to integrate the 1 over x cubed from negative 1 to 2. Okay, so don't just do the problem, find the antiderivative, and then plug in negative 1 to 2 in the antiderivative and subtract, because you get the vertical asymptote for the function of 1 over x cubed at x equal to 0, which is between negative 1 and 2. So this graph shows the graph of this function. It has two branches. One on the upper and one on the lower left. So this is the graph 1 of x cubed for this one function. It has two branches. And you can see at x equal to 0, it has a vertical asymptote for both branches. All right? So it has an infinite discontinuity at x equal to 0. And then you have to break up into two integrals. All right? So we need to integrate 1 over x cubed from negative 1 to 0, and integrate the 1 over x cubed from 0 to 2 and add them up. Fortunately, we don't have to do too much in this problem because we already did it. The second term on the right, the integral of 1 over x cubed from 0 to 2 from previous example. Okay, if you look at the previous example, that's the integral of 1 over x cubed from 0 to 2, and we know it's divergent or diverges. So the second term on the right, this problem just diverges as we did in the previous example. So then we don't have to continue because if one of the terms diverges, then we just conclude this whole integral diverges. You don't have to. The whole thing doesn't make sense. Okay, you don't have to do the first term on the left. So that's this example. Now let's do one more example with a double improper integral. So what does it mean by that? It means we have both type of the improper integral in one problem. Okay, so this problem we need to evaluate the integral of 1 over square root of x times x plus 1 from 0 to infinity. Okay, first you can see the upper limit of integration is infinity, so that is the first type of improper integral, right? But also at 0 for x, we got square root of x in the denominator. So if you plug in 0 for x in the function, you get 0 in the denominator, and that's undefined. So we got the vertical asymptote at x equal to 0, and that's the graph of the function if you look at it. Okay, it does have a vertical asymptote on at x equal to 0, and then you have another tail on the right. So this time we need to find the area under the curve, and it has two tails, one on the far right, one on the top. See? Well, you can start from either type. Okay. So for example, you can start this problem from the first type. So look at the infinity on the upper limit of integration, and then replace that by b, and integrate the function from 0 to b, and then take the limit from b to infinity. Okay, right? And then you just concentrate on the integral of the function 1 over square root of x times x plus 1 from 0 to b, and that itself is a second type improper integral. So you have to convert this integral as one with the function 1 over square root of x times x plus 1 integrated from a to b, and then replace 0 by a, remember, and then you let a approaching 0 from the right, if you still remember. Okay, then you can proceed with each integral, and take the limit. All right. So now, if you integrate 1 over square root of x over x squared plus 1, using substitution, it will equal to square root of x. Okay, again, you have to double check yourself at home. I don't have time to go through the details, but we talked about this kind of things before. So using substitution, you equal to square root of x, then you can find the answer for this integral, the antiderivative, to be 2 times arctangent square root of x. All right, for the x for substitution. Okay, And then just integrate from a to b and take the limit with a approaching 0 from the right. Okay, so plug in b and a for x. So we got 2 arctangent squared b minus 2 arctangent squared a. Okay, and then you need to take the limit with a approaching 0 from the right, and then after that you take the limit with b approaching infinity. Okay, so these are a few more steps. Okay, a few steps. All right, so then so you don't have to worry about the 2 arctangent squared b when you take the limit with a approaching 0 from the right. Okay, it has nothing to do with the first term. So, but when you take the limit of 2 arctangent squared a with a approaching 0 from the right, you just plug in 0 for a. So you get a square root of 0 inside. And then arctangent, a square root of 0 is just 0. And arctangent 0 is also 0. Okay, if you take a tangent is 0, you get 0. Okay, so that's why arctangent 0 is 0. The angle corresponding to its value is 0 is 0 degree itself. Okay, so then you got 2 times 0, so you got 0 in the second term. Then you only need to worry about the limit of 2 arctangent squared b for b approaching infinity. Okay, so when b get large, when you take the square root of b, that's large. So square root of b also approaches infinity, and then you try to find the arctangent function with the argument approaching infinity, and you get the power 2. Okay, as I think we showed the one example before, the curve of arctangent function. The angle corresponding to this infinity value. Okay, it's power 2. Tangent power 2 approaches infinity. What I'm saying is, so then that means arctangent square root of b is power 2 when b approaches infinity. Okay, that's how you understand the arctangent function. You try to find the angle with its with its tangent value approaching infinity, and that angle is power 2, or tangent power 2 approaches infinity. So then you get a 2 times power 2 minus 0, and you get a pi minus 0, so that is pi. So the area under the curve from 0 to infinity, okay, it is pi. So in this example, the integral converges. All right. Any